Hello everyone, my name is Hsuan-Chi, a PhD student at UIUC, working with Professor Sibin Mohan. Today I will present our work on Linux in Unikernel closing, where we essentially transform commodity Linux to behave like a unikernel with added benefits of ease of use, stability, and improved performance. This work is in collaboration with our colleagues at IBM Research, Daniel Williams and Ricardo Koller. Virtual machines are known to be heavy and inefficient. Unikernels are proposed to solve VM's problems, and unikernels are small and full specialized library operating systems that, by definition, contain only kernel functionality that is necessary for an application. Unikernels are known to have great benefits, including small image sizes, fast boot times, improved performance, and better security. On the other hand, developing applications on Unikernel is also challenging, since they have fewer resources available when compared to a general-purpose OS, such as Linux. For instance, they support fewer hardware components since drivers are not available and do not fully support the POSIX interface. Hermitax, a well-known Unikernel, supports only 97 of the total 335 Linux system calls. Applications running on the OSB Unikernel cannot fork or exif. Runtime can only run 37 curated applications. Essentially, the Unikernel community is unable to take advantage of the large amount of development in Linux community, in particular of the stable and well-known software and hardware support. In addition, the application must be specially developed or recompiled if it is to run on the Unikernel. In this work, we try to answer the question, can Linux behave like a unikernel and enjoy the associated benefits? We demonstrate how to achieve this by specialization and system call overhead elimination. These two are techniques derived from unikernels. Specializations makes unikernel contain only necessary code. Kernels and applications are linked together to avoid system call overheads. We call our reduced Linux lupine since it's a Linux in unikernel closing. Let's take a closer look at specialization. Lupine Linux is derived from MicroVM, which is a kernel specialized for serverless computing released by Amazon. MicroVM contains 833 kernel options. Although MicroVM is already specialized when compared to the off-the-shelf kernel distributions such as Ubuntu or Fedora, we still discovered 66% of the kernel configuration options are not necessary and can be removed. We refer to the remaining kernel as the lupine base. We categorize these removed options into three categories based on different unikernel characteristics. First, because unikernels are application-specific, we remove application-specific options that are only necessary for certain applications and may be reintroduced on top of the lupine base to create the final kernel configuration. Second, unikernels are intended to run only single one process at any point in time, so configuration options that support multiple processes such as cgroups and namespace are not required. Finally, unikernels are not intended for general hardware, so certain hardware-related kernel options such as power or CPU frequency management are removed from lupine. Now, we show how we eliminate the system call overheads. We adopt an existing patch called KML that enables normal user processes to run in kernel mode, since the process now runs at the same privilege level as the kernel. The privilege escalation host can be avoided. By patching the C library, the syscall instruction is transformed into the call instruction, and the function address is exported by the KML patch using vsyscall. Consequently, dynamic link applications can directly load the patch C library and run without modification or recompilation. We now show that lupine can achieve most benefits of unikernels, such as small image sizes, fast boot times, small memory footprint, and no system call overheads. and similar application performance. We studied the most popular 20 applications from the Docker Hub repository, and we found that only 19 additional application-specific options are needed to support these 20 applications, which dominates the downloads by 83%. We call the Lupine kernel, which is to run 20 applications, Lupine General. We compare our system against two types of cloud-based OSs, Linux-based and Unikernel-based. On the Linux side, we have Lupine and MicroVM. On the other side, we have various unikernels, including OSV, Hermitox, and Rumpron. We first compare the kernel image size. All systems are configured to run a simple Hello World application in order to measure the minimum possible kernel image sizes, plotted on the y-axis in megabytes. We also studied the effect on application-specific configuration options on Lupine image size. Compared to the Lomon Lupine, Lupine General shows an increase of up to 19%. However, Lupine General still remains much smaller than the corresponding OSV and Rumpron image sizes. So we show that Linux can be as small as or even smaller than unikernels. We now present a comparison of the boot times. The y-axis plots the time in milliseconds. Lupine boots faster by 2.8 times when compared to microVMs. When compared to other unikernels, Lupine does significantly better than OSV ZFS while having a performance that is comparable to Hermitox. The OSV measurement shows the dramatic effect of implementation choices. When we first measure it using ZFS, which is the standard file system for OSV, boot time was 10 times slower than the implementation using a read-only file system. We also find that even Lupine General boots faster than Hermitox and OSV. So Linux boot time is comparable to unikernels. For the memory footprint, we define the memory footprint for an application as the minimum amount of memory required by the system to successfully execute that application. Our choice of applications was severely limited by what unikernels can run without modification. So we only present these three applications, including Hello World, Nginx, and Redis. Unfortunately, Hermitox cannot run Nginx, so we omit the results in the graph. This graph shows the memory footprint for each of these applications. In both application-specific and general cases, Lupine achieves a memory footprint that is as small as unikernel systems do, while each of the unikernels shows variations in memory footprints. The Linux-based approaches do not. There is no variation because the Linux kernel binary is more or less the same size across all of these applications. We removed many kernel modules via specialization and showed that Linux can be very lightweight as unikernels in terms of memory footprints. Unikernels claim to exhibit low system call overheads due to the fact that application is directly linked with the library operating system. In this graph, we show the system call overheads tested by LM-Bench. The y-axis shows the system call latencies in microseconds. Using Lupine, a Linux system can achieve similar system call latency as other unikernel approaches. Experimentation with Lupine ignore KML shows that both specialization as well as the elimination of system call overheads play a role, and specialization contributes up to a 56% improvement over microVMs. We also measure the benefits of KML by calling system calls at different frequencies. We found that the latency can be reduced by up to 40% in the case where we call system calls very frequently, but this improvement vanishes very quickly in more realistic workloads. In summary, we show that Linux can be made to enjoy low system call latency, but system calls are not expensive as we expect. We now compare the performance for two popular web applications, the Nginx web server and the Redis key value store. The table lists the throughput for each system normalized to micro-VM performance. As we see, Lupine outperforms the baseline as well as the Unikernels. Also, Lupine General does not sacrifice any application performance. We attribute much of Lupine's 20% or greater application performance improvement to disabling security enhancements such as kernel page isolation or CGUPs, which is fine for single applications. The better performance of Lupine when compared to the Unikernels is most likely due to the fact that the implementation of kernel functionality in Linux has been highly optimized over the years, thanks to the large Linux community. The community of Linux is the biggest advantage of Lupine, and it is very difficult to create another kernel which is as optimized as Linux is. Finally, we show that our Linux-based system Lupine outperforms Unikernels in multiple ways. It can have a really small image size, boot very fast, and have a great application performance. Best of all, Lupine is still a Linux, and no recompilation or modifications to applications are required. Finally, I would like to conclude some insights that we have. First, specialization to Linux is important. Second, specialization per application may not be necessary. Third, system call overhead elimination may not be worthwhile. Finally, Lupine avoids common pitfalls. In the end of the talk, I would like to thank our sponsors, the Office of Naval Research and IBM Research. Our contact information is posted here, and please feel free to contact us with any questions or feedbacks. Thank you very much.